Hey, Dr. Clark coming back at you with another differential equations video. This one we're looking at section 1.3. And the check your understanding problem is a modeling problem. Suppose a large mixing tank holds 200 liters of brine at a concentration of 15 grams per liter. And another brine solution with concentration 30 grams per liter is pumped into the tank at a rate of 5 liters per minute. Simultaneously, the well-mixed tank is drained at a rate of 5 liters per minute. And they want us to model the mass of salt, A of t, in grams present in the tank as a differential equation together with an initial condition, and then sketch a graph of what A would look like. Okay, so if I think about the situation here, I have a tank with some water in it. There is a brine solution that's sort of being pumped into the tank, and the tank is also being drained out. You can, if you want, think that there's some sort of brine coming in, there's some brine in the water, and then there's some brine coming out. And what is nice about this problem is the rate in is 5 liters and the rate out is 5 liters, so the volume is going to stay at 200 liters throughout. So we don't have to deal with any changes in volume, but they're asking us to model the mass A of t of salt in the tank. So that is our differential equation should be dA dt equals something, and that's going to be salt in minus salt out. And there should be some A of 0, some initial condition to make it a differential equation. And we can figure that out because I think originally there's 200 liters of brine and it's concentrated at 15 grams per liter, and that gives us 200 times 15, which is 3,000 grams of salt in the tank. So A of 0 is 3,000 grams of salt. Okay? Now, what's going on here? At the beginning, the tank is entirely 15 grams per liter, but over time that 15 grams per liter kind of goes out and 30 grams per liter is coming in, so that the water is going to get saltier and saltier, and eventually it'll probably trend towards a 30 grams per liter concentration as all the initial water sort of gets pumped out. Okay, so what we have is we have 15 grams, coming in we have 30 grams per liter at a rate of 5 liters per minute, and you can see the units there. We're going to get grams per minute, and 30 times 5 is 150. So we have basically 150 grams per minute of salt coming in. So we can say the rate in is 150. It's a constant rate because it's a constant flow at a constant concentration. So the derivative here is constant, right? Derivative is constant because it's a constant rate in. The rate out, though, is a little trickier because whatever the current level of salt in there, it's not going to be a constant 15. It's going to get saltier and saltier and saltier. So there is some A of t, how much salt is in the tank. There is 200 liters in the tank. So the out here is going to be A of t over 200. That's the concentration. That's in grams per liter. And then it is 5 liters per minute. Again, the same rate out, 5 liters per minute. And so this works out to be basically 5A over 200. That's the rate out. And it's minus because that salt is leaving. So we get minus 5A over 200. And that makes a differential equation. It's an initial value problem because it's a differential equation together with an initial condition. So dA dt equals 150 minus 5A over 200, and A of 0 equals 3,000. That is our answer to part A. Part B says draw a graph of what A of t should look like and explain your answer. Okay, well, I know that A of t should start at 3,000, right? Because initially there is 3,000 grams of salt in the tank. In the long run, the water is going to be 30 grams per liter and a volume of 200 liters. So if I do 30 times 200, that is 6,000. So in the long run, it should work its way over to about 6,000 grams of salt in the tank. And I guess you could wonder, so my graph should sort of go up and over to 6,000. But I guess there's a little bit of question, does it start going up or does it kind of go like that? And we could think about that a little bit because we know the derivative is dA dt. That's 150 minus 5a over 200. So we can actually figure out the derivative at 0 is 150 minus 5 times the initial condition, 3,000 over 200. And if I do 150 minus 5 times 3,000 divided by 200, that is 75. So it has a positive slope to begin with. So my graph is going up and then leveling off at 6,000. And I would have to do probably some more work to figure out how long it would take to get towards 6,000. So I'm not really sure what to put on my t-axis other than it goes up and over to 6,000. All right, and that is the answer to part B of the Check Your Understanding problem for section 1.3.